In 2022, NASA's Juno spacecraft made a discovery about our largest gas giant that shook up everything we thought we knew about how planets form. And now scientists are no closer to figuring out what it means. They're at an impasse. So they've gone back to basics, running simulations on a supercomputer to get to the bottom of this conundrum. Their hope is that it will help unravel one of the biggest mysteries of the solar system. What's at the heart of Jupiter? I'm your host, and you're watching this channel. Join me today as we look into the latest computer simulation aiming to explain Juno's surprising discovery that Jupiter may have a very unusual and unexpected core. Let's start with a recap. You see, when Juno arrived at Jupiter in 2016, it brought with it a suite of instruments designed to finally answer the question of what is inside this huge planet. For decades before, scientists had assumed that Jupiter would have a solid core, much like the Earth, where all the planet's mass is made up of heavier elements like iron and nickel concentrated at the center. Scientists expected to find something similar with Jupiter, but instead, Juno found that it has no such thing. The evidence was revealed through the spacecraft's measurements of Jupiter's gravity field. Gravity fields around planets are affected by mass, both where it is located and how fast it spins. And while Juno was orbiting the planet, it measured variations in the magnetic field caused by the gravitational pull from the planet's atmosphere down to its core. By comparing those measurements with simulations, scientists could work out what kind of core Jupiter might have. Juno's findings turned that picture on its head because instead of confirming the existence of a dense core, its observations showed that there wasn't anything particularly dense at Jupiter's center. Instead, it revealed that whatever is at the heart of the planet is strangely lightweight. That suggested that Jupiter's core could be diluted with lighter materials like hydrogen and helium, or it could be fluffy, full of empty space. Scientists were totally shocked by the result because it completely went against the current understanding of planetary formation. According to that understanding, a planet's core forms first. It starts off as a seed of heavy elements, which then acts as a framework for the rest of the planet to build on. As the planet grows, lighter gases like hydrogen and helium gradually accumulate on top of the heavier elements until eventually they make up the bulk of the planet. But if that's the case, why wouldn't the heaviest elements sink to the bottom and end up at the center? The leading hypothesis to explain the results is that Jupiter's core has been squished into a pancake shape by some sort of ancient cataclysmic event. That's been tentatively dubbed the Big Crunch. Imagine an object roughly the size of Earth but made of heavy elements like iron and rock. If such an object had formed within Jupiter and sank to the center, the planet's material would have been crushed together, making the core bigger but not heavier. And that would explain why the core is relatively light. However, if it were true, then shouldn't we be able to spot the remnant of this big crunch somewhere in the planet? Unfortunately, no, scientists can't find any evidence of a large body inside Jupiter. All the mass seems to be spread evenly throughout the entire planet, or at least within half of its radius. And that brings us to the latest research. A team of scientists ran a series of simulations trying to figure out just how much of Jupiter's mass is contained within that inner half. The goal was to determine whether there really is a dense core lurking somewhere below the planet's clouds, whether it's buried deep under the surface or halfway between the center and the surface. They did this by simulating hundreds of scenarios to see if they could reproduce the gravitational data Juno collected. In each model, they varied how far down the heavy elements extended. And they also took into account Jupiter's rotation rate, which affects how far different materials can be flung away from the center due to centrifugal force. Interestingly, the team found that a lot of the models they tested were ruled out right away, because they didn't match another observation from Juno, namely the lack of an intense X-ray signal coming from Jupiter's core. It seems unlikely that any big object could have remained hidden from Juno's X-ray spectrometer. And that means that whatever is at Jupiter's center cannot be dense enough to block the X-rays. That rules out the possibility of a metallic core, which is one of the most likely places for all those heavy elements to gather. After all, metals tend to be dense. They have a lot of mass packed into a small space. And we know from studying Earth's core that pressure hundreds of thousands of times greater than the Earth's core actually squeezes the core of Jupiter's metallic hydrogen into a state of matter that is electrically conductive. If metallic hydrogen makes up Jupiter's core, then maybe it is mixed in with so much hydrogen and helium that it is diluted to show up as a distinct feature in the planet's gravity field. To investigate this, the researchers tested a variety of mixtures of hydrogen, helium, and metals and found that models with more than 40% of the mass made up of metals were rejected by the data. After ruling out metallic cores, only models in which the heavy elements were spread across the upper half of the planet remained a viable option. But then another problem reared its head. These models still produced explanations for Jupiter's gravity field that didn't fit with the observations. The models could get close, but they couldn't quite nail the observed gravitational signature. To get their model to match what Juno saw, the team needed to assume that these heavy elements only made up 5% of Jupiter's mass. But they already knew that couldn't be right. We know that Jupiter's core is made of heavy elements because it has been raining them down onto Earth. Back in 1997, scientists discovered an unusual spike in the number of beryllium atoms hitting Earth from space. Beryllium is a metal, and it's usually found on Earth as part of minerals. The atom is never found free in nature on Earth's surface because it reacts so quickly with other chemicals. But the beryllium atoms raining down on Earth were not attached to anything. To reach Earth, they must have broken free from a big body very far away, and the only likely candidate is Jupiter. We know it rains bertrandite on Earth because we've actually caught it happening. The Japanese Yoko spacecraft detected an increase in X-rays coming from Earth when Jupiter passed overhead in 1998, and the increase in beryllium atoms continued 4 months afterward. So we know that beryllium exists on Jupiter, but if it's only 5% of the planet's mass, like the models suggest, that means there's almost certainly a metallic core underneath. And yet that contradicts Juno's X-ray observations. This is the impasse I mentioned at the start of the video. Scientists have absolutely no idea what's going on, and this discovery has left more questions than answers. For example, if the heavy elements are spread across the upper half of the planet, what caused them to be distributed so evenly? Did Jupiter experience some kind of catastrophic event in the past, such as being struck by a giant protoplanet? Or did it accrete gradually from a disk of spinning gas, slowly pulling the heavy elements down to one side? These are the kinds of questions that are keeping scientists up at night, and it'll take years to answer them. Not only do scientists need to collect more data from Jupiter, they also need to improve their models of how planets form. What's clear is that Jupiter has a weird core, and it could have a much weirder history than anyone imagined. Maybe one day soon we'll learn that it was once home to a lost world. All the best with that. Thanks so much for watching, and I'll see you next time.